你去口袋，你说的是我吗？
我明诶啊，
I feel like on the way.
no. How's the midterm? How's the midterm? Hard or easy? So regarding the next quiz, right? I think don't have series, but not sure yet. Have to update you again when the time comes. Okay. Hopefully don't have, but final shouldn't have, I think. For finals. Yeah. Quiz, I'm not sure. Got enough things to test on. Yeah, so today we will finish up series with Fourier series. You don't need to copy anything. I think it's not tested, so I just quickly run through it, and then we will start partial derivative. Okay, so the material for this half of the semester, I think, will get a little bit harder. Okay, because you need the help of geometry to understand the question well. Okay, so we don't have Mike today. So I don't have Mike today. Okay, so let's recall what we did last time. Okay, so last time we have power series, right? So what's power series? We write a function f in the linear combination of power of x. Okay, so for example, c1 plus c0 plus c1x plus c2x squared and so on. You don't need to copy. I will give you all the answer for Fourier series. Okay, you can try do practice at your home, but yeah, so you just listen. Okay, so we have this power series. Now we want to consider Fourier series. Okay, so what's Fourier series? So we want to write our gx in terms of cos and sine function instead of x to the power n. Okay, so it looks something like this. Let's put an cos. Let me see. Cos. I think n pi. So I split out the constant term as A2, A0 over 2. Okay, so if you have learned linear algebra, right? So the first power series use 1x squared x cubed power of x to be the basis. Okay, and then Fourier series use cosine sine function to become the basis. Okay, but this Fourier series really only work for periodic function. Okay, so only when your function is repeating over a period, we can do this. We can find a Fourier series for a periodic. Okay. So one thing to note here is both of them are continuous. But periodic function might not be continuous. Okay. So you use a continuous function to approximate something that's not continuous, but it is periodic. Okay. Okay, let's see the real definition here. Maybe I go here. Okay, so the power series and Taylor series is based on the idea that we can write a general function as an infinite series of powers, right? This one we have gone through. So the idea of Fourier series is that we can write a function as an infinite series of cosine and sine. So the definition of Fourier series is a Fourier series is an infinite series designed to represent general periodic function. So see, if I combine these two functions, right, f and g, okay. So let's say the three green line, right, represent 1, 0, and -1. So when you add up, they get a different sum, okay, at every place. Okay, so for example, so if you look at this line, this x here, right? Okay. So here you get 1, okay. Here you get something 0.5. Okay. So if you add these two functions together at this point, what do you get? 1.5, right? Okay. So you can see that this point here is higher than 1. Okay. 1, 0.5, so you get 1.5 here. Okay. So similarly, if you add something positive with something negative, they cancel out. So for example, here, right? Okay, you get something between around 0.5, okay, then -1 from the other function, right? So when you add up, comes somewhere around negative 0.5. Okay. So look at this example here. Okay, can we use a sine wave to make square wave? First of all, is this a function? Why? Okay, cannot pass the vertical test. What's the vertical test? So for a single x, you cannot have multiple y. Okay, so this is not a function. Okay, but we can approximate this function using sine and wave function. Okay, so for example, we start with sine. Okay, you can see that this sine here. Okay, when it go up and go down, it follows this pattern, right? But you can see that there's some difference between the square wave and this sine wave. Right? There's still some difference here. Right? So we want to make this difference smaller, smaller, and smaller. Okay. So how to reduce the curve? How to increase the curve? We can add more curve, right? Right. You see just now, that's an example. When we add up these two curves, this part increases and then some part decreases. Okay, so we need to add appropriate curve. adjust. Okay, so how we adjust? So we add another term, sine 3x over 3. Sine 3x over 3. And then you can see that it approximates better than the sine x just now. You can see that there's more crest coming up. Okay? But you can see the difference between the square wave is getting smaller. They're getting smaller. Okay, we can keep doing this. Okay, we add sine 5x over 5. Okay, we got more crest, but the difference between square wave decreases more. Decreases more. Okay, and then we keep doing it. Okay, we keep adding the odd period. Okay, divided by the odd number. And then we can get something like this. Okay. Notice that this line here, right? This line here is never vertical. So if you zoom it further and further and further, right, you will still see this slanted line here. Okay, just that the gradient gets steeper, steeper, and steeper, but it never get to infinity, which is the vertical. This is the point here. Okay. So there are two functions here. One is the original square wave. The other is what we call the Fourier series. When we take this sum to infinity. Okay, here is just partial sum, right? We just stop at 39. But if you go up to infinity, is what we call the Fourier series. Approximate the square wave better. I approximate the original function vector better. Yeah. Okay. Yeah. So you can see that if I get up to 199, you can see that the crest getting smaller, smaller, and smaller, and smaller. Actually, this is how the light works, right? Light bulb. You know, the light bulb is using AC current, right? Okay, it's turned on and off, on and off, on and off, on and off, until the stage you cannot recognize it is turning on and off. And then you just see that the light is constant, but it's not. If your eyes is very good, then maybe you can recognize it. Okay. Yeah, so frequency. Okay. So what's the periodic function? So we can really only do Fourier series on periodic function. So periodic functions means fx plus p equals to fx. Okay. So for example, sine x and cos x are period function of period 2 pi. Okay. What does it mean? It means that fx plus 2 pi equals to fx. Okay. So meaning if you take this point here, compare somewhere other than 2 pi, they are the same. Then take here, 2 pi is the same. 2 pi is the same. Okay. 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 So 2 pi is the period. Okay. This one here. So how we produce periodic function in general? Okay. So we can really just take a function that defined on an interval. Let's call it minus L to L. Okay, what does minus L to L mean? So it is around the origin. Okay, L to the right minus L to the left, L to the left, L to the right. Okay, so this is the interval from minus L to L. Okay, so you can start with any function on this interval, and then you just repeat it over 2L. Okay, then you get a periodic function, right? Makes sense? For example, I do something like this, right? Okay, over 2L. Then how do I make periodic function? I just repeat this over and over again. So I can put this here. Then I repeat again. Keep repeating. Let me move to. So I can just repeat the diagram over 2L. Okay. Okay. Yeah. Yeah. Okay. So so the key point of this Fourier series, right? There are two things. One is the function, the periodic function. The other is called the Fourier series of the periodic function. Okay. Just now you can see that the periodic function or the periodic wave maybe is not function. Okay. But Fourier series of that function must be a function. Okay, it's a continuous function because we add up cosine and sine wave. Right. Okay, so this two is the key thing in this Fourier series topic. So actually we can given a function f, if we want to find the Fourier series, right? There's a formula to find what is an and bn here. Okay, there's a formula to find it where you need to use this integration. Okay, so you need to integrate your f over cos so that you can find what is an, and then integrate over sine, you can find what is bn. Okay. So for now, I think you won't appreciate this because you never have you done this kind of computation before? No? Okay. Yeah, you just listen first. If you really want to try out, you can try out the example. I will give you the solution. You can check. Yeah. Okay. So you just listen first. Okay. So if you want to find this A0, A0, AN, and BN, right, you can use this formula here. Okay. So why we can use this formula exactly is because of these identities here. Okay. So you can see that if you integrate different over different m and n of the product of cosine, you get 0. Okay. So when you try to find coefficient, right, most of the coefficient go to 0 so that you can find the particular one. You can see that only when m equals to n in the product, the integral survive. Okay. For the other one, we can say that they are out of sync. Okay, because if you have a cosine with different period, they are like out of sync. So when you integrate, you get 0. Yeah. So that you guys have similar stuff in probability theory, right? You look at the convolution of function, convolution, right? Okay, this is also similar to convolution. You take the product of function that's with different shift, right? Here is different period. It's also different shift, right? You get what I mean? Don't get what I mean? Okay. Okay, I'll let you see something. Okay, I'll let you see thing. Let me show something it's easier to show. Okay. Let's try to. Okay, maybe let's examine this statement here. Okay, so this statement says that for any non-negative integer m and n, then these two multiply to 0 when you compute the integral. So let's draw the cost function. Okay. So this says that if I multiply these two together. Multiply these two together. Okay, let me draw it on thing. Okay, so when you multiply these two numbers together, right? Okay. Somehow when you integrate over this interval, okay, you get 0. This is what this sentence want to say. And then when I say out of scene, right? So you can see that, how to say, so you can see that actually sine and cosine are the same wave, right? Just different, shifted by, okay. So sine is the cos function shifted by 90 degrees, right? So yeah, this is what I mean by out of scene, okay? So they are actually the same wave, but you shifted differently. Okay, so when you shift it differently and then you compute the product, you compute the integral of the product, you get 0 most of the time. And most of the time. Okay. Why is it true? You need to show it. But this is the segment I want to try to say. Okay. So the other statement is because since just now we know that, okay, just now we know that the sine wave is not a function, right? Okay. Sine wave is not a function. But if you look at the Fourier series of the sine wave square wave is a function. Okay. So you could ask how this Fourier series converge to f at every point. Okay. In particular, we can ask what happened to the Fourier series at this point here. Huh? Break. It doesn't break because when you add up continuous function, it's still continuous, right? So it won't break. So what's the value of it? Okay, what is the value? It's also not 0, but it is the mean. Okay, half of the sum of limit from the left and from the right. Okay, so you can see that the half of the limit from the left and from the right is in the middle. Is this in this case? Okay, I mean it's in middle in every case. Okay, so this is the middle, meaning your Fourier series must pass through this point. Okay, at minus pi. Okay, here is minus pi. You have to always pass through this middle point here. Okay, no matter how much you add to it. Okay, so similarly, it is happening at every point here. Okay, every point on the function, right? So if you take a point here, okay, you ask what happened to the Fourier series at this point. Okay, it is equal to the half of the limit going from the left and going to the right. Yeah, but it is the same in this case, so it's just that. Yeah. So this is the convergence theorem. So there's one example here. Okay, one example here. So consider a function which is 0 from -1 to 0, and then 1, 0 from 0 to 1. So we start with this function here. Okay. From -1 to 0 is 0. Okay, and then from 0 to 1 is 1. That's this function here. And then we consider it repeating over this interval of 2. Okay, fx plus 2 equals to fx. Okay. So every time I want to produce a periodic function, right, the easiest way is I tell you what happened within an interval, and then I repeat it. Okay, this is what this question doing. Okay, I have a pattern on over an interval. Okay, and then I repeat it over this interval of 2. Everywhere. Okay, everywhere is quite important here on the whole real line. Okay, we keep repeating it, and then we want to find the Fourier series of this periodic function. Okay, Remember that periodic function and Fourier series is different thing, right? Because what you're gonna produce later is a continuous function. Okay, here it's not continuous, right? So later what you produce is a continuous function. So you should imagine something like this. Right? Okay. Okay. So just now from just now. So what happens to this continuous point here? What does the value of the Fourier series give you? Huh? Who says 0 again? Huh? Yeah, so half of the sum of the limit from the left and from the right, right? So at this discontinuous point, right, from the left is what? Is 0. From the right is 1. So half of them. So 0.5. Okay. So I mean from this, okay, actually you cannot guess, but mathematics is symmetric. So we would like, I mean, we prefer, yeah, we prefer, is it prefer to be symmetric, right? It is symmetric, right? If it is half. Otherwise, yeah, I'm not sure, but yeah, I mean, I prefer it is symmetric. I think it's quite natural to converge to the middle of the limit from the left and from the right. Yeah. But in this case, it's true. Maybe in some cases it's not true, but I mean, in the case of Fourier series, it's true. In the case of Fourier series, it's true. Okay, so let's see what we produce. Okay, so this time we say that Fourier series have this form. So what is A naught, AN, BN? Okay, and so we have a way to find them. We need to use the integral way. Okay, to find AN, you need to integrate your fx multiplied by cos, and then integrate over your interval of your period. So the period just now is going from -1 to 1. Okay, so you need to integrate from -1 to 1. Okay, and then you do all these computation. Okay, and then finally you found something like this. Okay, this is what you found later. Okay, so you got a constant term part plus nothing from the cos part, and then something from the sine part. And then you can see that there's an alternating sign here, on and off. Okay, it's okay. You don't follow this calculation. I'm just telling you what to do. You can try it out. I will give you the solution. So in the end, you will get something like this. Okay. So this is built using sine. Is it convincing that this is a sine graph? Convincing or not? Right, because sine graph is like this, right? But it is shifted. So shifted up. Okay. Shifted up already. So it's above 0. Already get shifted up. Okay. Yeah. So this, if you like, you can use this grapher in future if you want to deal with this Fourier series stuff. Okay. So you can plot the partial sum. Okay, plot the partial sum. You can see that slowly it converging to the square way. You can see that this graph here is a bit misleading, right? Okay, because you see that there's a vertical line here. But if you zoom in, and further, you can see that there's a bit slanted. A bit slanted here. So a bit slanted here. A bit slanted here. Okay. And you can never get this non-function thing from something that's function. Okay. You only get smaller and smaller approximation. Okay. What time? Okay. In fact, do you guys know even function or odd function or not? No, huh? Okay. So then I quickly go through. So even function is a function that satisfy f minus x equal to fx, and odd is fx equals to minus f minus x. Okay, so odd or even function. So the miracle here is we can just approximate the even function using cosine wave, because cosine wave is even. Okay, we can approximate even function using cosine wave. And if you really do the computation, right, you try and find the coefficient of sine is actually 0. Okay, so we can approximate even function using cosine wave because cosine is also even. Similarly, you can only approximate or find the Fourier series of odd function using sine wave. Okay, because sine wave is odd. So it is enough to use odd function to make out odd function. And it is enough to use even function to make out even function. Okay. Okay, so you can, if you like, you can try these examples. So one of the useful things of these examples, right? So is to if you evaluate at certain point, you will get this interesting result. Okay, you will get some infinite series equals to some irrational number, right? Because irrational number you can't express in terms of fraction. Okay, so how to find irrational number? You don't have calculator, right? You don't have calculator. How? You can somehow, sometimes will pop up in some of the Fourier series. Okay, when you evaluate your series at certain point, okay, you get some interesting identity here. How do I actually? Oh, I mean, let me see. In this case here, okay. So where does the pi pop out? You mean is it? Yeah, sometimes it pop out when you calculate the coefficient. Yeah, when you calculate the coefficient, like the coefficient is the integral over some let's see. So in this case here, you can see that where does this pi pop up? Okay, this pi number here pop up when you compute the constant term of your Fourier series. Yeah, constant term of your Fourier series, right? So remember that we have a function. Okay, so this is the story you need to keep telling yourself. I got a periodic function. Okay, I want to find the Fourier series of this function. Okay, I want to approximate the periodic function using continuous function. Okay, and then the formula is a naught over 2 plus linear combination of cosine wave, okay, and linear combination of sine wave. Okay, so your constant term, so all these coefficients, right, you can compute as a integral. Okay, integral of what? Integral of the periodic function multiplied by cos or sine, depend on an or bn you want to find. So if you want to find an, okay, if you want to find an, you need to multiply with cos. And then differentiate over the interval minus L to L. Okay. So what's the interval of minus L to L? Is the pattern that you want to repeat. Okay. That gives you the period. And then A0 is relatively easier because you integrate at cos 0, which is just integrating fx. Okay, so you are computing the, not the area, but the integral of fx all from minus L to L. Okay, so this pi number or some irrational number might pop up when you do this integration. Okay. Okay. Yeah. But if you want to try out, you can try this example. So next part is this Fourier cosine or Fourier sine series. So what's Fourier sine or Fourier cosine series here? Okay, so it is also the question of extending the function. Okay, but there are two ways to extend the function. Okay, there are two ways to extend the function. So let's say we have this example here. It is x from 0 to 1, and it is 2 minus x from 1 to 2. Hey, it's up. This is the function appear in the probability here. Oh no? Do all of you know the function? So you integrate the convolution of. So you integrate the function. What you call? You call that the. What's the distribution? Cumulative. The f. So you have this fx plus y of a. What do you call this? Not each convolution. I mean, what's this? X plus y. Oh, a.
Joint distribution.
Joint distribution. Sound closer. Joint distribution. Joint distribution. Okay. Right. So you met this kind of function before. Okay. But here, okay. Oh, I saw you from your textbook. Your friend showed me. Huh? Yeah. Okay. Okay. So there are two ways to extend this. Okay. Just now what we did is we just repeat this pattern. Okay, to build a periodic function. But there are actually two ways to do it. Okay. One way we can do it evenly, which is what we did just now. The second way is you can make this extension here. Okay. You can see that the first one satisfies fx equal to f minus x. Right. So if you take an x here, okay, and then you consider minus x, they are the same point. Okay. And the odd case, if you take an x here, and then you take a minus x here, you can see that they are negative of each other. Okay. So these are two ways to extend this particular function here. Okay. So you might ask, so how to do this in general? Okay, how to do this in general? What you do is you what? No formula. Okay, so what you do is you use this these two theorem here. Okay, you use these two theorem here. Okay, you use this theorem here. Two theorem here. So if you want to make it an even function, okay, you just compute what is this Fourier series. Okay, and then you see what's the shape. And then if you want to extend it oddly, okay, you just compute the Fourier series of the odd function, and then you see what's the shape. Okay, so the first one will give you the first shape, and then the second one will give you the second shape. Okay. Okay. No. I mean, of course, you don't know what is happening, but you need to you need to understand what's the procedure. That's all. Again, maybe you don't know why give you those things, but you need to at least follow what is happening. Yeah. Okay. Because you haven't tried the calculation, of course you don't know. So you need to know the instruction first, and then you try, see if it works. Okay. Any question? Next chapter. Before next chapter. Any question on this Fourier theory? Huh? Okay, so far. Yeah. Yeah. Okay. I think this part is not tested, so we just run through it. Okay, for your future. It's like I think Fourier series is kind of useful. For you. Huh? Yeah. frequency stuff 啊。Okay. How about we take a break until 8:57? Yeah. Before we start the new stuff.哎，
就期中考试就是有道题上算面积的，然后道题上背景函数应该是cos2西塔，然后我最后检查的时候，就可能检查太快了，然后我背景函数弄错，就是我以为我原来做法错，我一开始用cos2西塔题的，然后我以为我弄错，然后我就写成tan2西塔，然后那个答案全改掉了，然后就改错了呀。然后我后面回到宿舍的时候，回想起来我好像用错了，然后就是他好像可能题，我这样做会给几分？
我也不清楚哎，我要看一下啊，那几题哈。
我那答案被我划掉，你可以看到正确答案，但是被我划掉，全改了。
这样有一点难哎。
他5分的话，大概能拿几分？
我也不清楚哎，那是第几题啊？
就是让你算那个面积的题，就是他那个3.2西塔跟3.2西塔围起来那8块面积。
那是其他老师改的，
其他老师也不是你看
啊，不是我改。
反正
先看一下。Hello. I don't have mic here. Can you help bring one mic? Because my mic battery dead. Thank you. Yeah, I mean，对，我呀，再看吧，再看呀。我们派回来讨论看咯。但是你如果划掉的话，就真的应该没有什么课。
他你2分同情会不会给他？
不清楚哎，我要看一下。
无所谓，反正就5分到。OK，看过。不是，然后那个就是这个物业题目它是不考的是吗？
应该是不考吧？
那下次 quiz 它那个范围是什么？
对，还不确定。
还不确定。
嗯，
但是我看你那个不是，
他写什么？有 series 吗？
好像没有，就是他不是写了 quiz 3那个考范围
？quiz
3，不是，我记得好像我之前看到过一张表，就是
对。
他那个是就是那个范围是吗？还是要改的？
可能会改，我到时会再说，看下他们怎么决定。呀，看他们。
其实我感觉当时就是我检查的时候只剩10分，然后太贪了，
然后
有点想拿满分了，我就那个，然后就看一下那个小分道题再提一遍，结果当时可能只剩3分钟，还2分钟，然后一眼看歪了，然后就把那背景改掉，其实给我感觉对，当时就觉得那种当时就感觉已经脑力不够了，还一检查。
哎，谢谢。谢谢。哎，好了，这是你的麦，原本的麦，我麦没有电池，可以借吗？可以。等下我还回去给你们。这样子啊，要记录下来。哎，等下我回去还给你们。好。昨天我2点的时候按没有人来。是啊。哦，不知道。昨天没有在。OK。
然后代入面和卷积公式有没有什么几何意义？
什么叫展积公式？
那个卷积，什么
是卷积？
有 convolution。
convolution 有啊，你可以去看那个 YouTube。
几何意义是什么？
几何？我想一下。没有，他在看他还有几何意义的我想一下。他就是在算它的重叠吧，不然你给我想一下。有一个好理解，就是我现在不太记得了，你可以去看有一个 YouTube。 YouTube 你有一个叫 Tree Blue 吧，你找 convolution，我曾经看过，但是我忘记了。他解释到还挺好，因为他也有 animation。啊，哎，这个很好，这个很好，这个很好，这个很好，好，啊，这个挺有趣啊，这是我忘记了。挺好。
熟这个照片我没看过，
是我同学，
为什么是你？
因为我还认识他。哦，这个你觉得吗？
哪一个带过来？高级
高啊什么？
不是高是高级，就是高年级。
比我大吗？
我不知道他比大不大，还第二还是第三？
真的吗？
真的？
为什么跟我一样209哎？
没有，哎，喂，
是209成原样了。
那他209不在我班上，
真的吗
204吧
？204吗？
是好的204，很细那个。
就是国内的，就数学老师每个人的发音都不一样。对啊，
细吧？
我们叫什么 sigma？
是呢，是另外一个画法的。
真的吗？我忘记了。
这个有好几个画法的。
对。对，我记得
老师，打算用 Fourier series 画模嘛？
是的。
可以就是用 Fourier series 画，只能画 period 的东西。没有诶，画模。对啊，大家。哎呀，Fourier transformation。假设的 Fourier transformation 算是另外一个。对。我可以画，但是我是说，他画的这个东西，如果画成等角，应该别说了。真的吗？马上一对比，但是后面更平。
肯定没有，就是我带过来，我是新买的。
我那一次来了，讲看
就是谁都不知道。
都是讲，这个我知道去不一样。
没事，便宜点。
Science 跟 Math， computer science 也做。哦，是啊。哦，哎，那是什么啊？那我觉得有的没错，好几个他们也是看，教 YouTube 教 YouTube 他居然我们那些的数学，他被顶了。我知道，他被顶了。那偏方教授，大家叫做偏方，你要给钱，主题的，对啊，他什么都教。就慢点，反正都慢点，慢点。有啊，
没有考，
应该没有考，
应该啦，
这就应该有考就要再讲
应该你。要努力争取啊，
你很会啊，你
你要努力争取啊
努，力的考
就是怕我给你考一个0分哦。
微笑啊。Okay, let's continue. Hello. Okay, let's continue. So what have we been through? What have we been through? What's the thing we do first in the class? Chapter 10. What's chapter 10?
Oh.
Polar coordinate. Okay, polar coordinate. SY curve. Okay, and then we parameterize curve. Okay, using time. Right. Okay. And then what else? Vector function. Okay. 3 variables using just 1 variable. So let's write down. Okay, so we have a vector function. Right. The functions. So we have 1 variable to 3 variable. Right. So we trace out a curve inside 3D space. Okay. We also study surfaces in 3D, right? So for example, we have f xy equals to, sorry, f xyz equal to 0. So surfaces in R3. Okay. Anything else? Anything else? Yeah, surfaces, all the quadratic surfaces, conic section also, right? Faces. Is it quadrant? Yeah. What else? Series already? Series. Okay, and then we go to series. Sequence, okay, sequence first, good. You need to define sequence first before you define series. So sequence is what? Is actually a function from n to r. Okay. So you guys see quite a lot of mathematical object now, right? Different mathematical object. We have sequence first. Okay, let's call it a n. Okay, an. And then we have series. Okay, series where we sum all the an together. Okay, an. Yeah, we sum all the an together. So what we're really interested is actually the power series. Okay, because we write our function from R to R to be a infinite sum. Yes, infinite sum of scalar multiple of powers of Sn, s to the power n. Okay. Okay, so this is so far what we have been. And then we just finished at the, just quickly run through Fourier series, which is infinite sum of cosine and sine wave. Cosine and sine wave. Okay. Okay, so now we want to do calculus. So we want to do calculus on functions of two variables. Function of two variables. Okay. So what does function of two variables means? I have a function from R2 to R. Okay. I have R2 to R. So what does calculus mean? Anyone know what calculus means? Wow. How you know? Okay, I said before, very good. So it's the infinite study of the space. Okay, infinite study. So you zoom in and in and in. So you see what happened locally. Okay, so we will see what are we trying to do. Okay. Okay, so we start with this partial derivative. Okay, why partial? Because now we have more dimension now. In one dimensional space, you only can do dy dx. Only one direction you can go. Okay, but in two dimensional, you can have two direction at least. Right. Okay, so let me give you some pictures here. So let me give you some picture. Okay, so if you only have y and x, okay, if you differentiate dy over dx, right, okay, there's only really one direction you can go, up to scalar, okay? But if you are a function of two variable, your domain become two-dimensional, okay? Your domain become two-dimensional, right? Okay. So you can go different way, okay, towards a point, okay? So let's say, for example, so here I want to call to the point x equals to 1, okay? So there are literally one way up to scalar, okay? Up to scalar, there's only one way, okay? From left or right, okay? This is up to scalar. But in 2D, you have a lot of way to go to a single point, okay? And you can take different paths to go to this point, okay? You can go around and then come back, also can, okay? Like the exponential to the theta, right? You can use that path to go in, also can, okay? In 2D space, right? So, actually one thing I want you to imagine, okay? There's one thing I want you to imagine here. So let's say I look at, so now I keep comparing what is happening in one variable and two variable case. So for example, if I look at fx equal to x, so what's this graph here? Fx equal to x. So it's just the diagonal line. Okay, fx equal to x. Okay. How about fx? Let's look at what shape we want to see here. Let's look at I think we learned a few functions here, right? What thing we want to look at? Circle, circle, circle. Let's see what to see. Uh, Let me think. What's the good shape here? Huh? Healing the let me think. Fx equal to xy. Let me see. I have example or not. Let's just take xy equals to 0 or 2. Okay, let's put 2. Fxy equals to 2. What's this shape? What's this constant shape here? Hey, hello. Wait, too excited already. So what is this? Ah, what shape? No. Any point I put in, I get 2. Right? Not straight line. Huh? What? Not a line. So what's your domain in this case? It's different domain. So let me put different G. Okay, different function. So the domain is everything in R2. Okay. So every point I have 2 on the third axis. Right. So every point here, everything in my domain, I got 2. Okay. So it's a plane. Okay, so it's a plane at 2. Okay. So it's a plane at 2. Right. Okay. So how you should think of this function, right? You should see what is your domain. Okay. For example, here is this R. So R you can think of as a line. Okay. So how this line sit in this R2 space? Okay. So we call this a graph. So we call this, so let me write this. So we call this a graph of F. Okay. Graph of F is X and Fx. Okay. So graph of F live in R2, which is R plus R. If I write plus, you will, I just put R2. Okay. So in this case here, graph of G, where does graph of G live? You have xy and fxgxy, right? Gxy. Can live in R3. Okay. So do you ever ask a question? This is a function from R to R, right? Why I draw this R2? Why I have 2 axes here? Okay. So what are you doing is you are sketching the graph. Okay. And then this graph live in the total space of these 2. So how many are here? 2 are. Okay. How many are here? 3 are. So this is called the graph of F. Right. Sketching the graph. So what does sketching the graph mean? Okay. So the graph live in the total space of these 2. Okay. Can understand this? So now I want to give you a concept is what is the domain? Okay, you look at the domain. This function tells you how this domain sit inside the total space. Okay. For example, this F here is taking the whole real line, sit inside R2. So how this line sit inside here? So it sit as a diagonal line. Okay. How about a function from R2 to R? Okay. R2 is what? You can think of it as an infinite plane. Infinite plane, right? Okay. How does infinite plane sit inside R3? Okay. So now it's just sitting like a sheet. Oh shit. Like a sheet. Okay, a sheet of paper. Okay. Right. flat at the point at the height 2. Okay, so you can imagine that you can bend this shape, right? So there are different ways how this paper sit inside R3. Okay, imagine. Well, let's imagine this paper here. Okay, you imagine this paper is a R2. Okay, S10. Okay, just now like this, it just sit like flat. Okay, sit flat. Okay, maybe sometimes you can sit like this. Then you use a different function to represent, or it's sit like something like this. Also can. Okay, so this is everything we need to consider in this subsection here. Okay. So when we take difference derivative, right? So we can go different way. How to flow down? Okay, you can think of it like flow along the mountain or the valley, the gradient, the slope. Okay, how sloppy is it? Okay. So this variable of two function, you can use it to model the mountain, right? You just consider how steep is the surface. If you don't care about what happened inside, okay, the surface, okay. So mostly we will deal with surface, but sometimes we will extend it to 3D, three-dimensional. Okay, so a real value function of two real variables is a function that assigns to each ordered pair xy in some set D of the plane a unique real number. Okay, so this is just a definition of a function. I give you an input, you give me a unique number, right? The vertical cast. Okay, one input only have one output. Cannot have one input, two output. Okay, one input, one output. But now your input have two numbers. You need to tell me two numbers. So fxy equals to x squared plus y squared. So if you want to evaluate at x, y, so xy equals to 1, 1, what do? You just input the number x equals to 1, y equals to 1, and then evaluate, which you get 4 in this case. Okay. So in this case, you can plot out the surface and then see how it changes over all the xy inside your domain. Okay. So the set D is called the domain of the function. If it is not specified, we just take it to be the natural domain, the set of all xy in the plane for which the function rule makes sense. The range of a function is its set of value. And then some terminology we call xy independent and then z dependent. Okay. If we can write z equals to f of xy, right? Because they are xy are independent, because z is equal to this variable, right? So z are dependent. So we take an example. Is it example now? Not yet. How about we skip this one? I thought about this. So let's see what I mean by natural domain here. Okay. So natural domains means all the points such that this function makes sense. Okay. Let's look at this fx y. Okay. It is square root x plus y plus 1 over x minus 1. Okay. So does this function make sense of every point in R2? Why? Huh? We will get something over 0. So we need to exclude what? 1. Anything else? Negative value of? Sorry, this is 1, right? So we need to exclude 1. Anything else? What do you mean by negative value? Huh? Or subjective? Anything else? Anything else you need to exclude? X plus y plus 1 should be larger or equal to 2. I'm sorry, 0. Okay. Because negative, you won't have square root. You have square root of negative number, but that number will live in complex. Okay. But we only care up to real for now. Okay. For this topic here. So we only care from R2 to R. So it doesn't define on whole R2. So it only define on a domain, the largest domain it holds, which we call the natural domain. Okay. So the natural domain is what? So the natural domain is all the xy such that x is not equal to 1 and x plus y plus 1 is greater or equal to 0. Okay. Anyone know how to draw this domain? How to represent this domain here? Anyone know how to represent this domain? Huh? How to represent this domain? Can you draw it up? So S cannot be equal to 1, right? So S equals to 1 is what? It's a straight line in R2. So we want to throw away that line. Okay, so let's plot this one here and then we throw it out. So when we throw it out, usually we put dash. Okay. How about S plus Y plus 1 equals to 0? What's that? A function. So it's also a line, right? Okay, it's also a line. So where is the x plus y plus y equals 0? So it's y minus x minus 1. So is y equals to minus x shifted down by 1. Okay. So y equals to minus x is something like this, right? But shifted down by 1. Okay. So shifted down by 1. But we not just only want this line equals 0, right? Anything greater than it, we also accept. Okay. So greater than it is the left side or the right side? Sorry, right side of the left side. Right side. Okay. So it's on the right side. So it's everything here and then exclude the line x equals to 1. Okay. So to plot the z, right, you need to create another axis and then you need to see what happened here. Okay. You need to create an extra axis to see it. This is just the domain. Okay. This is just a domain. So let's say if you want to evaluate the function at 3, 2, okay, you just simply substitute your x equals to 3 and then y equals to 2. Okay, so this is simple, I guess. So get square root 2 of 6 over 2. Okay. Okay, next. How about this? What's the natural domain for this? Does it define on whole plane or not? No. So what's the restriction here? You need to make sure that y squared minus x is greater than 0. Okay. So let's say we want to plot this domain out. How does it look like? Okay, so you need to plot what is s squared minus x equals 0 first. So what's that hyperbola? Like this, like this, like this, or like this. Up, down, or left, right? Left, right, okay. Left or right? Left meaning like this, left. Right. Okay, it is right. That's right. Okay, so this is the shape. Okay, y square equals to x. Make sense or not? Y square equal to x. Because when you square y, right, you get positive x. So positive x is on this side. Negative x on the other side. Okay. Okay. So positive x on this side, negative x on the other side. So s square plus s square equals to x is all positive on this side. Okay. But you only want x square minus x greater than 0. Right. So is it on the left part or on the right part? Okay, it's on the left part. Okay. Is it clear why? Is it clear why? Not clear? Okay. So for example, you take one number here. Yeah, just now I also skip this. So let's use this example then. So if I put 1 here, okay? Put 1 here. I also got 1 here, right? Okay. So anything above here, right? So anything above here is what? So let's look at the point here. What is this? So let me write down first. Y square minus x squared 0. So how to check this? So how to check this? Huh? Sorry?
Greater than y squared.
Okay, so where should we start? What's your suggestion? Where should we start? 1, 0. So where's 1, 0? 1, 0 is here. You mean here? 1, 0. Okay. Okay, y square equals 0. So y square is minus x is minus 1, which is less than 0. Right? Is it clear? Okay, so let's take a point here. Okay, let's take a point here, which is 2, 1. 1, 2, sorry. 1, 2. Okay. So we need to check whether 2 square minus 1 is greater than 0 or not. Right? Okay. So in this case, you get that 3 greater than 0, which is true. Okay. But if you take anything inside the parabola, okay. For example, Jinghua said take 1, 0. Okay. Then you compute 0 square minus 1. Is it greater than 0? Okay. Is 0 square minus 1 greater than 0? Okay. You will get minus 1 greater than 0, which is a contradiction. Okay. Is that okay? So you need to take any point inside the shaded region, okay? And then you verify that y square minus x is actually greater than 0. Okay? Is that okay? Question? Got question? Seems like I go a little bit fast already. Okay, let me show you one example, right? Let's try one example. Let's go back to the easiest case. Okay. Y equals to x. Okay, y equals to x. So where is y greater than x? Where is y less than x? Okay. So on this line, right, what do you have? You have 1, 1, 2, 2, 3, 3, 4, 4, and so on. Okay. So when is y greater than x? Okay. So if you consider everything on the right of this line here, Okay, what are these points? So these are 1, 0, 2, 0, 3, 0, and so on. Okay. So these are all the points that are satisfying y less than x. Okay. And on the other side of x equals 0, you will get y greater than x. Right. So if you verify what are the points on the left, for example, you will get minus 1, 0, minus 2, 0, and so on. Okay. Is it? So you have two different regions here. Is it okay? Is it okay? Okay or not? Believe or not? I show you some point already. Some of the point. And then if you want to show it rigorously, they have to do some work. But I show you some example here. Some point here to convince you first. Okay. Yeah, how this line split into this inequality. Okay. Okay. It's okay. So one quick way is you just take one point and then check it. What kind of inequality is satisfying? Okay. 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 All right. So just now what? Yeah, we'll decide this. So continue. So let's keep going. Okay. How about this? So similarly, how about let you try? Try 3 of this. Yeah. You try 3 of this. Give you 5 minutes. Try 3 of this. Three of them. I think you guys prepare better than the other classes. They don't bring their lecture notes. You guys all bring your lecture notes. Some of you even printed out. Serious, huh? Yeah. No, I mean, so far, for those I teach, right? I mean, I think the only class I see people printed out is your class. I think they just use computer, they just use iPad, tablet. Still very old school. You guys are old school. Old school. I'm also old school. Huh? I know. I use tablet because I have to project. Already, I got me. No. But you want to sponsor me, is it?
哪里？啊，新的啊？
Yeah. My screen broke. So no choice.
要买就买啦，我都骗你啦。
小看老师的实力啊！
Huh?
我玩那个白天，
What?
白
Yeah.
我就上啊，我一个礼拜。
Broke screen break already. Screen break already. What? Oh, what do you mean? How? Break already? Screen break already. The screen. Yeah. Not worth. Okay. Okay, let's start. Okay, continue. So what's the natural domain for square root y minus x squared over x squared plus y minus? Huh? Oh, you mean this one, is it? Y squared. Okay. So what's the restriction here? Why? Okay. There's another restriction coming from the denominator because you don't want the denominator to be 0. Okay, you don't want this to be 0. So only one way to get 0 is when x equal to 0 and y equals to 1. Okay, so you don't want this. Okay. Don't want this. Any more restriction from this function? Numerator, any restriction on it? The square root function cannot apply on negative number. Okay, so you want to make sure that everything inside the square root function is greater or equal to 0. Okay. Okay, so how you draw that region? So when y equals to x squared, okay, I believe everyone of you know how to draw it, but you need to decide whether it is the top or the bottom not included. Yeah, so why is it true? Because it's wrong, it's true. Okay, so you need to take a point here, inside here, and then verify. Okay, take a point xy, and then verify that actually y squared is greater than x. Okay, so yeah, okay. So for example, take any point here. So let's call it a 0, 5. Okay, is it true that 5 squared greater than 0? Yeah. Okay, so everything above. Okay. And then not that we exclude the point 0, 1. Okay, we exclude it. Okay. We have this parabola, hyperbola or parabola? Parabola, okay, parabola. Okay, and then we exclude the 0, 1. Okay, excluded. Is it okay for this case here? So you have D, all the xy. So this is the set notation. This is set notation. All the point, okay, to be complete, I would say this xy is live in R2. Okay, what condition you have to satisfy? Y greater or equal to x2, and also x not equal to 0, y also not equal to 1. Wait, let me see. I think these two have to put together. Okay, these two have to put together. Okay. Otherwise, exclude too many things. Or I just say xy not equals to this point. Yeah, 0, 1. Okay, like this. Clearer. Okay. Okay, how about the next one? Also, you met a square root function. Okay, you have to make sure the things inside the square root is greater or equal to 0. So in this case here, you get 9x squared plus 4y squared less than or equal to 36. So what's this shape? Quadratic surface. Ellipse. Okay, ellipse, right? Because you have different coefficient in front of x squared and y squared. So this is an ellipse. Okay, so you got an ellipse here. Okay, and if you draw out the z-axis, actually you get a hemisphere, not hemisphere, ellipsoid. Huh? What we call that again? I forgot the name. One dimensional higher than eclipse. Ellipsoid. I think it's ellipsoid. Ellipse, not eclipse. Ellipse. Okay. I think it's called ellipsoid, if I'm not wrong. Okay, half of the ellipsoid. Okay. Remember, right? Remember this or not? This square root function thing. Last time we also have this for our circle. Right. Remember this circle stuff? Let me redraw this circle. Okay. So if we want to draw out this semicircle, right? Okay. We also can write it as y equals to square root 1 minus x squared. Okay. So you can see that this is a one-dimensional higher surface. Oh, yeah, shape. Okay. So you can think that we can increase more terms and more terms, and then you will get something in higher and higher dimension. Okay. I mean more quadratic term. Okay. And next, square root 9 minus x squared minus y squared. Okay, you also need to make sure everything inside the square root is greater or equal to 0. So in this case, you get x squared plus y squared less than or equal to 9. Okay, so what's this? Just circle? No, too big. Yeah, inside the circle. So if you fill the circle, you get a disk. Okay, you get a disk. Right, so if you have circle, okay, with radius 9, so it's 3, right? And then you want everything inside here, you get a disk. We call it this, right? Now no more this DVD player, huh? Did you guys see this before? No? Okay, hopefully. I think next generation never see, right? Okay. Okay. For this. Okay, okay. Okay, so I keep this as exercise, then we'll provide solution later. Midterm again. Okay, so for the rest, right, I leave at exercise and then we'll provide solution. So let's go to next topic. Okay, come back. Okay, so next, the level curves of a function f of two variables are the curve with equation f(x,y) equals to k, where k is a constant in the range of f. And we call this curve as contour plot. Okay, contour map. Hey, hello. Okay, come back. Okay, so given z equals to fxy, okay, each horizontal plane z equals to k intersect the surface in a curve. The projection of this curve on the xy plane is called a level curve. So what's level curve? Okay, so we got a fxy, right? We got a fxy, and then we cut it as k. Okay, when we say we cut it at k, right? We cut it at the plane z equal to k. Remember just now we started with a plane fxy equals to 2. Okay, so now we consider any k, not just 2, 3, 4, 2.5. Okay, so I will use the plane and cut through the surface. Okay, So for example, in this diagram here, you can see that this is like UFO. Okay, it's actually not UFO, but you can see that this is a plane get bent up. Okay, right. Okay, you just imagine this is a plane get bended. It is not solid, it's not filled. Okay, it's just one surface like that. Okay, and you use a plane to cut it through. Okay. So you can see that when you cut it through at different level, what you will get? At the top, you get a point, right? And then slowly, when you cut lower at a lower height, you can see that you get circle that gradually increase in radius. All right, okay. So we will plot all these curve as our level curve or the contour plot. Okay. Have you seen this in your geography book? Yeah. Okay. So what you do is you take a sheet of paper. Imagine a big sheet of paper, and then you put it on the mountain. Okay. And then you keep the shape. You take the paper up or the surface up. Okay. And then you cut it through every level. That's why we call level curve. Huh? Why you want to squeeze a mountain? Then mountain is gone. What shape you get after squeezing? No. You mean okay, you can imagine that way. Yeah, you can imagine that way. Yeah. Right. So okay, good point here. Okay. That's not squeezing the mountain, but you kind of flatten it. Okay, you flatten it. So you should imagine how I recover the mountain shape from this map. Okay. So the only information I need to tell you is what is the height of every level curve. Then you can regenerate the mountain. Okay, so I just need to tell you what is the height of every contour here. And then the height will help you to decide what's the 3D shape. Okay. Can you imagine? So if I don't give you this shape here, right, I just give you a bunch of circle. Okay. And then I tell you what is the height of each circle. Can you reconstruct this shape here? Can, right? Okay, yeah, you just depend on the height, and then you need to lift up the circle, and then you join them together because it is continuous. Okay, we deal with continuous function, so you can join them up. If it is not continuous, you cannot join. Okay, but in our case, it's continuous. Okay, so these are some examples. Okay, for example, this is a mountain. Okay, there's one tree here. Let's cut this tree away. Just look at the mountain. So you can look at different level here, okay? And then you can draw the contour map up. Okay. If I told you what's the height of each contour here, then you can really reconstruct this mountain. Okay. Similar to this cone, 3D cone here. Okay. So even yeah, the height I mean is f x y equals to k, right? So this is a height. Sorry. Yeah. I mean, yeah. Wait, what happened? What's happening? Okay, so the k is your height. So you can see that z equals to s squared plus y squared, right? Plot out a surface here. Okay, but when you fix k, okay, you cut out a level curve. Okay, you cut out a level curve. Okay, so let's try an example here. So I let you try. Cut out at this 4 point. What do you get? Let's try compute this. Okay, so try and do this for computation here. So what do you get? What do you get? I think you get bunch of line. You get bunch of line. Okay. Wait. You just guess or you don't just guess. Okay, so these are lines. So what are these lines? So let's see what are these lines. Where are these lines? Okay, y equals to minus 3 over 2x. Okay, it is just y equals to minus x slanted a bit more. Okay, and then shifted out differently. One shifted by 6, one shifted by 3, one shifted by 0. So there's one of them is here. Okay, one of them is here. And then one shift down by minus 1. Minus 3. Okay, so something like this. So two of them at the both at the top. And then like this. Okay, so this is the control map. Okay, so how to reconstruct the surface? You need to consider the what's the key to reconstruct the surface? K, what's K? Is the height. Okay, the height. So you can see that. So here we got height equals to minus 6, 0, 6, and 12. Right. So we got different height here. So which one is higher? So the bottom one is higher, right? Okay, and then you go down and further down. Okay, so what's this shape? Not staircase. Log. Okay, so what's that shape? Okay, you should imagine more because we are continuous, right? So you should fill out all the space here. Okay. So what's that? What's trapezium or not like that? It's not like that. So you got the infinite lines, okay? And then this infinite lines going from the top to bottom. Yes, a plane. A plane is a plane. Yeah, you feel the below. No. Yeah, that's the point. So this is just a surface. You don't need to feel inside. So, okay, there's nothing inside here. When you see this surface, right, there's nothing inside here. Okay, we don't care about the things inside. We just care about the surface. You should think about the paper, how the papers cover a surface. Okay, how the sheet of paper cover. Okay, so this is a plane. Remember, hey, see, you still remember the plane equation or not in the exam? Plane equation. What's this plane equation here? Is 3x plus 2y plus z equal to 6. Right? Okay. So what's the normal vector? Yeah. What's the normal vector? Okay. So this is a plane. Okay. This is a plane. So right, if you have a plane, you cut it with another plane, constant plane, you get a line. Right? So this is the plane. So this function is a plane. So f x y is a plane. Do you want to do one more and then we finish there? Let's do one more and then we finish here. Okay. So this one. Okay. So if you compute k equals to 0, 1, 2, okay, so let gxy equals to 0, gxy equals to 1. Look at a different height. Okay. you can see that you get a circle. Okay, circle centered at the center with different radius. Okay. So can you imagine what is this shape here? So where's the highest point in this case? 3, right? So here is the highest one. And then you gradually go down, the radius increases. What do you get? Huh? Sphere. No, not sphere, not quite sphere. Huh? Not quite sphere. Huh? Cone. Because this is quite symmetric, so we call it a hemisphere. Hemisphere, half of the sphere. Hemisphere. Yeah. So we only get half of the sphere. Okay, top part of the sphere. So we only get the top part. Okay. So we get something like this. So we get this. Okay. Yeah. So what is level curve doing is you cut it through at every level. Okay. You cut it with plane. Right. You cut it. So you cut it. Okay. So when you cut it at the top, you just have a point. And then slowly the circle get greater in radius. Okay. So why we interested in this level curve? Because we can reconstruct the surface using the control map. I just need to tell you what's the key? Height. Okay, I just need to tell you the height. Okay. The height is hidden in the number. So that's why we are obsessed with number. Okay, it's okay. Okay. See you next time. See you next week. Okay, bye. Hey, 翻译翻家咩？哎。